Namaste everyone. Welcome back to this lecture on mathematical foundations for machine learning. Uh, we are in week 10 and we've been looking at matrix derivatives. We saw in the last lecture matrix derivatives, and we saw the idea of a vector valued function, and we saw that to be a matrix transformation of some vector. The input vector gets transformed to another vector, let's say y, through the matrix A. So we basically had a mapping from Rn to Rm, and we saw like how do we do the gradient for each of those functions, and in that process we looked at two different types of layouts, namely the numerator layout and the denominator layout, where we said that okay, it depends on how we are going to arrange the gradient, the elements of the gradient vector. Are we going to arrange it as a row vector, or are we going to arrange it as a column vector? If it's a row vector, we call that as the numerator layout, and if it's the column vector, we call that as the denominator layout. And then we figured out a couple of interesting properties which we would be using further for our understanding of couple of concepts which we have actually studied before. Right, we've studied the idea of least squares, we've studied the idea of principal component analysis, and those things we'll be studying here with respect to the concepts from calculus. So that's what we'll be doing in the rest of the week. On that note, what I'll do is like I'll start with the idea of optimization. I'll just give you a brief introduction to what is optimization, constraint optimization, and unconstrained optimization, and so on. And then we will take up this case study of, let's say, least squares and of course what's that, principal component analysis and so on. Okay, so let's go ahead with the idea of optimization in the first place, and then I'll come back to the idea of matrix derivatives to look at the notions of what would you call the least squares and stuff, right? We'll look at that. So the first thing that I'm going to do now is I'm going to talk about optimization. So what is this optimization all about, and why is there so much of emphasis on optimization, especially in machine learning? Right? This is something which we need to answer. Now, optimization is something all of us know. Either we maximize or we minimize. Sometimes we maximize or minimize things with no conditions or restrictions, and sometimes we operate within certain restrictions, and within that boundary that we have, how are we going to maximize or minimize and so on. A good example is like when you say you just have 4 years of undergraduate engineering degree. I want to maximize my learning. So what is it that I can do in the 4 years so that I learn more, right? So you have a constrained problem there, you have constraint optimization problem there, because the time that you have in your academic institution for an undergraduate studies is just 4 years, and there's the constraint on time, and you want to maximize learning within that time. So you have constraint optimization technique that constraint optimization. Whereas there could be other cases where there's no restrictions at all, just need to find out what are the parameters which would maximize or minimize a function. So on that premise we are going to get into the idea of this optimization things. So the first thing we are going to ask is like, what is it that we call, what is it to say optimize? The second thing that we are going to ask is, what are we going to optimize? The third we are going to ask is, with respect to what are we going to optimize? And the fourth thing that we are going to ask is, are we going to have some kind of a constraints or a set of constraints or no constraint at all? So these are the things that we are going to look at, right? So let's look at this. So what is optimization? So it basically some kind of it's what do you call, it's a journey towards finding the best solution to a particular problem. So it involves finding the best solution to a problem. best solution to a problem, right? And what does the problem basically involve? This problem basically involves, let us say, set of variables, then you have a set of constraints. I mean, it is not something new to most of you. Probably you would have done a preliminary course on optimization, or a part of optimization. You would have studied topics like your simplex method, and you have your dynamic programming and so on. We are just going to extend those ideas. So, we have set of constraints. Yeah, fine, we have set of variables, set of constraints, but there must be a function too, and you say functions, right? Best solution to a problem which will involve a set of variables, a set of constraints, and a set of functions, right? Okay. So, the first thing that we want to look at is this function. We have a name for this function. So, the function that we want to optimize is actually called as the objective function. Objective function is the function that we want to optimize. That is nice. Function we want to optimize, okay, and the set of variables. So, either optimize, let me put it a bit more clear. Let us say, look, this optimization can be maximizing or it could be minimizing, right? It could be optimize, I mean, could be maximize or minimize the objective function. That is the goal, that you want to maximize or minimize. And you have what are called as decision variables. You have what are called as the decision variables, which are basically the variables that you adjust, variables that we adjust to optimize the objective function. Right, and then we have what we call as constraints. So, we have what are called as constraints. These are basically the restrictions that we put on the decision variables, restriction on the, let us say, decision variables. Right, this is basically you have certain set of conditions, like what I told you. You just have 4 years time, and you want to maximize your learning. So, what are the parameters that are involved in all those things you just say. So, these are basically the constraints we have. Okay. So, do all the optimization problems involve constraints? May or may not, right. So, let's first of all, let's try to say this. So, optimization problems, first of all, let's say optimization problems may or may not be, may not involve constraints. Right, it could involve it need not just be what would you call a function of single variable, it could be function of multiple variables too. So, we write this as it may involve one or more decision variables. Right. Another good example is like you would have seen in cricket matches where they say like, look, I have like power play 6 or 5 overs or power play or whatever, and that means I have 30 deliveries, and in 30 deliveries I have to maximize the runs that I score, right. So, that is another optimization problem, right. Okay. So, this is what we have. So, what do we mean by unconstrained problem? It is like let us look at this. So, an optimization problem statement could be something like this. So, let f of x, I am just giving it in a single variable right now, we will later convert it to we could actually see the function involving multiple variables in some time from now. So, let f of x be the objective function. In machine learning we call this as the cost function, right, objective function. So, what are we going to do? We are going to say maximize f of x, right, and what is the parameter x that maximizes this function, or we say minimize f of x. What is the value of x which minimizes? Find that value of x which would minimize the function f of x, right. So, when I just write this maximize f of x, minimize f of x, this is going to be, I do not have any kind of restrictions on x. So, there are no restrictions on x. No restrictions on x, and such optimization problems are called as unconstrained optimization problems. Right. Let us just basically look at a simple example, a toy example for this. So, let us take f of x is equal to x squared. Now, what I am going to do is I am going to say minimize. What is the minimize f of x, which is nothing but minimize x squared. This is what we have. So, how do we go about doing this? This is just something which I am recapping from whatever that you have studied before. You take the first derivative of the function, equate that to 0, then what you do, take the second derivative of the function, plug in the value of x that you have got when you equated the first derivative to be equal to 0, and then plug that value into your second derivative. If the second derivative value is greater than 0, then you say that look, I have got a minima there. If the second derivative value is less than 0, you say that there is a maxima out there. So, what are we going to do? We are just going to do a few things. Before we solving this, let us recap what we have done. So, I mean you have done before, I am just going to say this. So, to minimize or maximize is basically find out that parameter x which would maximize or minimize this function. Now, what we are going to do is how are we going to check whether it is going to be minima or maxima? So, what we do is first, I mean of course, we assume that f of x is like continuous and it is differentiable and stuff. So, we say first find out df of x by dx, right, and equate df of x by dx, df by dx to 0. Let us say you get a value x star here, right, you get a value x star. The solution to this equation is basically x star. Now, what you do is figure out d square f of x, d square f by dx squared, evaluate at x star. If d square f by dx squared of x star is greater than 0, then I will put less than 0 here, so that we address both the cases. If it is greater than 0, then you call that as a minima. If it is less than 0, you call that as a maxima. Now, why do we say this? Second derivative greater than 0, you have a minima. Second derivative less than 0, you have a maxima. First of all, we must understand, we will go back to this. We are equating d f of x by dx is equal to 0. That means you are hitting a point at which the slope is 0. You are hitting at a point where the slope is 0. That means you have actually, you are looking at the function at a particular point, which is like when the slope is 0, that means it is going to be horizontal. So, you say that the slope is 0. Now, what is happening at that point? Now, what you do is you look at the rate of change of rate of change. So, d square f by dx square is nothing but d by dx of df by dx. That means you are looking at the rate of change of rate of change. So, what are we of the function? So, what are we going to do? If this basically is greater than 0, then we say that it is a minima. The slope of this, the slope of the slope is going to be increasing. Therefore, we say that we have attained a minima at that particular point x star. Similarly, if d by dx of df by dx, that means the slope of the slope is going to be less than 0, what are we going to say? We have hit a maxima, and from there on you are going to get a negative slope, which means you have hit a maxima, you have hit a peak. Now, it could also be equal to 0, in which case you just call that as a critical point. Of course, we have when you look at multivariable function, this is going to be a bit different. We have a different name for this. We are going to give different name for that. So, let us look at that. Okay, fine. So, we were trying to optimize this function f of x equal to x square. So, we were basically trying to minimize x squared this constraint. So, what I will do is I will do this business of taking the d by dx, the derivative of this function x squared. We know the derivative of this function is, let us say, 2x, and if I equate this to 0, I end up getting x is equal to 0. Now, we see d square by dx squared of x squared, which is nothing but 2, and this is greater than 0. Then you say that x squared has a minima at x is equal to 0. Now, if you substitute the value of x equal 0, you basically get 0 comma 0. This is you already know what shape is this going to be, right? We have already done, I mean, you know this. Okay. Now, there is a so we understand like what happens. Let's take a simple. So, let's just make a what do you call? Let's just make a comment here. So, comments before we go ahead. In fact, these are so we will say this f double dash of x, which is nothing but d square f by dx square, is basically the rate of change of rate of change, rate of change of rate of change. Right. Basically, it tells us how the slope is changing, how the slope is changing. Okay. So, what are we going to do? We are going to make these two comments. We are going to say f double dash of x f double dash of x is less than 0, means you have a maxima. That means the curve is going downwards. F double dash of x greater than 0 means you have a minima, and the curve goes upwards. right. This is what we have. Let us just look at this now. Let us take another example where we are just going to look at simple function f of x is equal to x cube. F of x is equal to let us say x cube. Now, we know the derivative of this, we get df by dx is equal to 3x squared, and if you equate this to 0 you end up getting x is equal to 0, and d square f by dx square, if you see, you get differential of 3x squared, which is nothing but 6x, and at x is equal to 0 d square f by dx square is also 0, right. So, the function f dash, you say it does not have, I mean it neither has a maxima or minima at x is equal to 0. So, what we are going to do is we are going to conclude this. We are just going to say f double dash of x is equal to 0 at x is equal to 0, and it has neither max or the neither maxima or nor the minima. Nor the minima at x is equal to 0. Right. Take one more function and then you will probably understand it better. We are going to take example f of x is equal to x power 4. So, f dash of x is basically df by dx, which is 4x cube, and that if you equate it to 0, equal to 0 implies x is equal to 0, right. So, what is f double dash of x? F double dash of x is basically 12x squared, which is equal to, at x is equal to 0 will be equal to 0 again. Now, one thing that we want to see here is whenever x is greater than 0, f dash is greater than 0, whenever x is less than 0, f dash is less than 0. So, note f dash of f dash is greater than 0 if x is greater than 0, and f dash is less than 0 if x is less than 0, right, or because the critical point that we have is x is equal to 0. So, what we say is we are going to call this these things to be the local minima and local maxima, right. So, what are we going to do? We are going to say that if this is the case, we are just going to make a small modification here. We say that f double dash of x less than or equal to 0, let us call that as the local maxima. F double dash of x is greater than 0, then we call that as the local minima, right. So, that is what we are going to do. Now, but this what would you say, this unconstrained optimization problems, typically what we do is, like in case of machine learning and stuff, you always have the notion of constrained optimization problems. Let us probably do one more thing. Let us take another example of unconstrained optimization problem and then check this. Okay. Let us take up this example 4 or example 5. Okay, another example. F of x is equal to x cube plus 11 by 2 x squared plus 6x, let us say plus 3. So, this is the objective function we have. So, I want to look at optimize this function. So, I am just going to try to optimize this function. So, what I am going to do? I am going to do the derivatives, the first derivative and the second derivative. So, let me take df of x by dx, which is nothing but 3x squared plus 11x plus 6, and that I am going to equate it to 0. Now what I am going to do is, if I equated the 0, this is a quadratic equation, therefore I will have two roots for this. Basically I can write this as 3x squared plus 9x plus 2x plus 6 is equal to 0. So I have 3x into x plus 3 plus 2 into x plus 3 is equal to 0, which implies x is equal to minus 2 by 3 and x is equal to minus 3. Now what I am going to do is, I am going to check what is happening to this function at these 2 points, basically the points x is equal to minus 2 by 3 and x equal to minus 3. So let us do that. So I am going to do d squared f by dx squared, which is nothing but 6x plus 11, and I am going to look at d square f by dx squared at x is equal to minus 2 by 3, which is nothing but 6 in, so I am going to look at 6 into minus 2 by 3 plus 11, which is basically 11 minus 4, which is basically 7. And similarly I am going to look at d square f by dx squared at x is equal to minus 3, which is 6 into minus 3 plus 11, which is minus 7. Now at the point 2 by 3 minus 2 by 3, I have my d square f by dx squared to be greater than 0, and at the point x equal to minus 3, I have d square f by dx squared to be less than 0. So what are we going to say? Let us say f double dash of minus 2 by 3 is greater than 0 and f double dash of minus 3 is less than 0. So what are we going to get? If this is the case, so what are we going to have? Whenever f double dash is greater than 0, that means I have a minima there. Whenever my f double dash is less than 0, that means I am going to have a negative slope, and therefore I am going to say that I have a maxima there. So let us check this. So at this point minus 3, I am going to have a minima, and at that point minus 2 by 3 I am going to have a minima, at minus 3 I am going to have a maxima. So let us see what is the value that we get of the function, right. So let us look at the function now. Let us go put these numbers and then check. So I am going to have at x is equal to minus 2 by 3, I am going to get something. What is that? Substitute in this function f of x is equal to minus 2 by 3 the whole cube plus 11 by 2 into minus 2 by 3 the whole square plus 6 into minus 2 by 3 plus 3, which is basically minus 8 by 27 plus this is 11 by 2, and there it is going to be 4 by 9. So it is going to be 22 by 9. I am going to have plus 22 by 9, and then I am going to have 6 will go minus 2 times. So you are going to have minus 4 plus 3, and if you do the computation you end up getting 31 by 27. So at x is equal to minus 2 by 3, this is the value that I am getting. Now at x is equal to, let us say at x is equal to minus 3, we have f of x is equal to minus 3 the whole cube plus 11 by 2 into minus 3 the whole square plus 6 into minus 3 plus 3. So if you do it, you basically get 15 by 2, which is 7.5, right. So this is going to be a maxima. You can clearly see in the graph that is shown that the maxima occurs at x equal to minus 3 and the minima occurs at x is equal to minus 2 by 3, and the values are 31 by 27 minima and 7.5 to be maxima. Okay, fine. Now that is good. So we know without any constraints we are going to do this. Now, what happens if you add constraint to it? What happens when you try to do a when you try to add another constraint to the problem as such, like how are we going to even work with it, right. So, let us look at this. Now, what I am going to do is I am going to move on from the idea of unconstrained optimization problem to a constraint optimization problem, and we will try to solve that using our Lagrange multiplier and so on. So, what we are going to do is I am going to move on to constraint optimization problem. So, what does this constraint optimization problem do? It basically tells us, look, there is a boundary within which you have to operate. I give you the objective function and you have a boundary within which you have to find the maxima or minima of the function, right, and you have the parameter which are going to give you the maxima or minima. So, that is what you are going to do, right. Okay. But in this case what I am going to do is I am going to adopt a different approach. I am going to take a multivariable case and try to address this problem, in which case all that we have studied in terms of single variables, now that has to be converted to a multiple variables case. Only then you will be able to figure out the idea of constraint optimization problems. It's easy for us to go forward. Okay. So, how are we going to do this? I'm okay. Let us look at this. Consider, or let us say this, let f of x comma y be equal to x y, right, f of x comma y be equal to x y. Now, what I am going to do is I am going to give a constraint. What I am going to do is I am also going to say that, look, maximize f of x y, maximize f of x y is equal to x y, subject to the constraint. I am going to have a constraint, I am going to give you a constraint which says, let us say x plus y, subject to the constraint let us say x plus y is equal to 100. Let us just put this, x plus y is equal to 100. So, what I am going to do is I am going to take a function x y where I have to maximize this function, and constraint is basically x plus y is equal to 100, right. Now, how is the function going to look like? What is the graph of the function, and what is the graph of this equation x plus y is equal to 0, and what are we trying to figure out with this? Is that clear? So, that is what we are going to look at. So, the constraint is basically this. Essentially, you can look at x y, when you say the product of two numbers, you can actually take it to be the area of, say, some rectangle, and then now I am going to say what is the constraint? The constraint is the length plus breadth should be equal to 100, right. So, that is what I am going to do now. Great. So, how are we going to do the optimization, and we are going to look at this, right. So, I have this function which is the solution. Let us look at this. I have this function x y which I want to maximize, and from this constraint I can write y is equal to 100 minus x, right. So, we write, let us write this. So, from the constraint we have y is equal to 100 minus x. So, now what am I supposed to do? I want to do this maximize x y subject to the constraint x plus y is equal to 100, but y is equal to 100 minus x. So, what I am going to do? I am going to say x into 100 minus x. So, that becomes my objective function now. So, I am going to maximize this x into 100 minus x. So, that is what I am going to maximize this. So, what am I going to do? I can find out this is nothing but 100x minus x squared, right, 100x minus x squared. So, what am I going to do? I am going to have this. Let me take the derivative of this. Df by dx is equal to 100 minus 2x, right. 100 minus 2x, if you equate this to 0, I get let us say x is equal to 100 by 2, which is 50, right. So, if I get x is equal to 100 by 2, which is 50, I can always find y, which is going to be 50 another 50, right. So, which implies this implies we will come back to this. First of all, we do not know whether that is the maximum value or whatever, maximizing is happening or not, we do not know. Let us look at d square f by dx square. D square f by dx square is basically minus 2, right, and this value is less than 0. Therefore, at that point x is equal to 50, I have a max, but now it is not at x is equal to 50, because I have a constraint which is x plus y is equal to 100. Therefore, what do I have? Y must also come into picture, therefore, y must be equal to 50, right. So, what I am going to have? This means it confirms it is a maxima, right. So, if we want to maximize, f is equal to x y subject to x plus y is equal to 100, x must be 50 and y must be 50. You can actually take this 50 into 50 is going to give me 2500 here, and any other value is going to be less than 2500. So, the max is going to be that, right. Great. Now, what we want to do is we want to go a step further. What is it that we want to do? We want to check, is there any other way to do this? If it is the case, how are we going to do it? Is there a way in which we can convert this the constrained optimization problem to an unconstrained optimization problem, because that seems to be a bit simple. Is there a way to convert this constrained problem to an unconstrained problem and solve it? And if we are able to solve it, can we extrapolate, can we use the same idea for, let us say, multiple variables and so on, and that is what we are going to do in our next lecture. So, in this current lecture we understood what is it to say optimization. You have an objective function, you have decision variables and so on, and we said that this you have to tweak around with the decision variables so that you get to the maxima or the minima of the objective function, and when you do not have any constraint, then you call it as an unconstrained optimization problem. Suppose you restrict the value of your decision variables to say some region or say some boundary, then I am going to get into the notion of constrained optimization problems, in which case I have to adopt a different strategy. We just done a simple example here. When we come back in the next class, we will figure out how to use what we call as the Lagrangian multiplier to convert a constrained optimization problem to an unconstrained optimization problem, and then we look at multivariable optimization problem, which is actually the bread and butter of machine learning topics, and then we will look at as I said, least squares and PCA. Namaste.